Here we are going to look at another application of the Taylor series and series in general. We're going to use them to approximate an integral that would be difficult to do with the regular function that was given and the limits of integration that are given. So one more time, the reason that we're trying so hard to find out if these series converge or diverge is to be able to apply them to rewrite functions as polynomials. That'll make it a lot easier to do general math with. So in this case, our integral goes from 0 to 0.28, ln of 1 plus x squared. Both the limits of integration and the integral itself are going to make it difficult to evaluate. And they want an error that's less than 10 to the negative 4. So two things to keep in mind before we jump into the problem is, one, the Taylor approximation for the ln function of 1 plus x is the alternating series x minus x squared over 2 plus x cubed over 3 plus ... plus -1 to the k plus 1, x to the k over k, which simplifies to the summation k equals 0 to infinity of -1 to the k, which is making it the alternating series, and that should be k plus 1, sorry, x to the k all over k, and that's true for any x that's less than infinity, so essentially any x. The second thing to keep in mind is that the error in an alternating series is less than the magnitude of the first neglected term. In other words, that means to be able to get our error less than 10 to the negative 4, what we need to do is go out enough terms so that the last term is less than 10 to the negative 4, and then we cut that term off and look at the terms before it. So for example, if our third term is less than 10 to the negative 4, then we would not need to include it, we would just include the first two terms. So let's go ahead and look at this integral and how it simplifies using the Taylor series. The integral is 0 to 0.28 ln of 1 plus x squared dx. We need to plug this in with the Taylor series that was given, but ours has an x squared and theirs has an x. That is a simple change to make. Since we have an x that is essentially any x, it's not going to be affected by changing this to an x squared. So all we need to do is double all of the x's that are given in the series or the summation. So I'm going to rewrite this 0 to 0.28. I'm going to start by writing it out as individual terms and carry it on with the ... So anytime I have an x, I'm going to double it because I have an x squared to work with. So this is x squared minus x to the 4th over 2 plus x to the 6th over 3 plus, and I'll just stop there, ... And we'll start the integrating, and then we'll check to see if we've carried out enough terms. So this integrates to x cubed over 3 minus x to the 5th over, so that would be to the 5th, and throw that in the denominator, times 2 would be 10, plus x to the 7th, that's a 7, throw it in the denominator, times 3 is 21, plus ... and we're going to integrate that from 0 to 0.28. So let's check for our error. If the value of this last term is less than 10 to the negative 4, then we've gone out far enough, and we can just deal with the first two terms. Okay, we would definitely want to check to make sure this term isn't also less than 10 to the negative 4. We might have to shave another term off. So let's just check our x to the 7th over 21. Plugging in our value 0.28, remember the second value is 0, which is going to make the whole term go to 0, so we only have to worry about the 0.28. To the 7th over 21, and using a fancy calculator, which is just Google, to do that math, we get 0.00000064252, which is less than 10 to the negative 4. This would be a 10 to the negative 5 number. Just to make sure that our term before that wasn't also small enough, we're going to check x to the 5th over 10, plug in 0.28 to the 5th over 10, and that would give us 5.00011721, which is greater than 10 to the negative 4. That's a 10 to the negative 3 magnitude. So it looks like we need the first two terms, and our error will stay less than 10 to the negative 4, because the error is, as we said, less than the magnitude of the first neglected term, so the first term that we're not going to include. So our approximation would just require 0.28 cubed divided by 3 minus 0.28 to the 5th divided by 10. And simplifying that math, we have 0.00714523. So in summary, we were able to approximate this integral by rewriting it as a polynomial and plugging and chugging with that polynomial, carrying out only two terms. We were able to approximate this as 0.28 cubed over 3 minus 0.28 to the fifth over 10, which was about 0.07071. And we knew that this error would be less than the error that they required because we went out one more term and double checked that that next term, or the first neglected term, the first term we don't include, had a magnitude that was less than the error. Okay, if you have any questions on this video, use Pronto or Hey Professor or send me an email, and I look forward to hearing from you.